For this homework video, I'm going to do it in two parts. I'm going to go through the first page with you, and then I'm going to do a little bit of notes, and then you can do the next two pages on your own. First, I'd like to talk about exothermic versus endothermic reactions. Endothermic reactions will make heat. If you see heat or feel heat that happens during a chemical reaction, this reaction is endothermic. Endothermic reactions result in a decrease in potential energy, becoming more negative. Stronger bonds are formed, and when stronger bonds are formed, the potential energy is converted into heat. When you burn gasoline, that's an exothermic reaction. When you burn wood, that's an exothermic reaction. Anything that happens spontaneously on its own without the need for an external energy source to sustain the reaction is an exothermic reaction. If something just gets hot in the sun, but it doesn't produce heat from a chemical reaction, it's not exothermic. In contrast to this, we have endothermic reactions, where they take in energy from the surroundings. It requires a constant source of energy in order to make the reaction happen. The energy that's taken in raises the potential energy. Endothermic reactions are a lot harder to see than exothermic reactions because you can't see the energy being transferred into the molecules. Oftentimes, it comes from the surroundings. So let's say you have a beaker with some water in it, and there's some reaction happening here. RXN means reaction. If it's endothermic, it's going to take in energy from the water around it. Endothermic reactions always involve breaking bonds and replacing them with either no bonds or weaker bonds. Less stability, higher potential energy. The way this is going to work is I am going to read off a few scenarios here. You pause the video and in your space over here, determine whether or not you think it's endothermic or exothermic, write a small explanation, and then I'll talk about it. The first example is the melting of ice is an exothermic or endothermic reaction. Explain. Melting of ice is an endothermic reaction. As we saw in the phase change diagram, when ice is melting, there is no change in the kinetic energy, the temperature. All of that energy going in is going into breaking hydrogen bonds. Breaking hydrogen bonds requires the input of energy, and they're being replaced with no bonds. They're just being broken. So this is an endothermic reaction. Number 2, is heating a stone in an oven an exothermic or endothermic reaction? Okay, you do it in your space first. Because there is no reaction here, it's neither. It is not an exothermic reaction or an endothermic reaction. You're merely increasing the kinetic energy of the stone. You are not changing the potential energy. The only way potential energy can change is if bonds change. PE is in bond. Example number 3. The reaction of zinc with hydrochloric acid, exothermic or endothermic? You did this reaction in your mini Hindenburg labs where you created the hydrogen balloons. The reaction became very hot to touch. I don't know if you remember. So what do you think it is? This reaction is exothermic. The products are lower in potential energy than the reactants, and it produces heat, and this is an exothermic reaction. The last one is photosynthesis. Is this exo or endothermic? Explain. Carbon dioxide and water are two extremely stable molecules. They are the product of every combustion reaction. So knowing that, and knowing that sugar and oxygen are high potential energy molecules that humans get energy from, this is an endothermic reaction. It's why plants need sun to do this reaction, because it requires the input of energy, and that energy is coming from the sun. All right, so that is the end of part 1. I'm hoping you have a good grasp on endothermic and exothermic reactions now. Let's talk about what to do with a chemical equation and delta H. So delta H, the delta stands for change, and H you can think of as heat, but in reality it's something called enthalpy. enthalpy. It is the heat of the system. So delta H here is the heat that is produced from this reaction, negative 154 kilojoules per mole. The negative sign is only indicative of exo or endothermic reactions. If you're doing this reaction and it produces energy, and you're writing that it's producing energy, you should write that in a positive fashion. Change the sign. But when it's written as delta H, if it's exothermic, it'll be negative, and it's positive endothermic. You can use this number to do stoichiometry. So for instance, let's say you had zinc, and you didn't have 1 mole of zinc, which would produce 154 kilojoules of energy. Instead, you had 2 moles of zinc. You can use this number as a conversion factor. You can multiply this number by 2. 2 moles of zinc will produce 308 kilojoules of energy. You could also start in grams. Let's say you had 5 grams of zinc. How many kilojoules of energy would this 5 grams of zinc produce? Well, first you would need to convert this into moles because the conversion factor is in moles here. 1 mole of zinc is 65 grams times 154 kilojoules per 1 mole, and that will get you 11.8 kilojoules of energy produced from 5 grams of zinc. So this is just another conversion factor that you can use in stoichiometric calculations in a balanced chemical equation. All right, you should be able to do the rest of the homework. Good luck.